attending today. And just a quick check, can everyone hear me?
I can hear you.
Laura, am I coming through clear?
Yes.
Yes.
All right, perfect. All right, so today we're going to be covering what we call building lifecycle impact, understanding the impacts of building design. So a quick course description. We're going to be looking at one of the most critical things that we face as a society today, which is our planet's future. So what we're going to be looking at specifically today is the carbon impact of building materials. So what we want to look at is finding viable alternatives to material selections and system assemblies to reduce negative impacts on our environment. And in terms of what we want to take away from today is really what we want to understand, what we want to let you guys understand is what's the importance of a life cycle impact for building materials, what tools and methodologies are available today, and then what makes up the life cycle impact analysis, and then also what's the benefit of a life cycle impact assessment in terms of designers and the building industry as a whole. And really to understand sort of the importance and the prevalence of a building life cycle impact assessment, we kind of have to look at where we are right now. The crisis that we're facing as a society, as a species in many ways, is a very time-sensitive one. If we look at a lot of the projection scenarios, IPCC has set 2020 as our best chance to make the most amount of change. Really, we need 2020 to be the peak of our emissions. So this needs to be the worst that we are, and everything has to get better from here. And so what that means is that the changes we make today will count to more to the solution than those tomorrow. This is something that I tend to understand a little bit like the time value of money, as anyone who has a 401k or a retirement account. The money that you're investing today is going to matter a lot, it's going to count a lot more as the years progress. And that's very much the same way with what we're seeing with the measures that we're taking today and the decisions that we make today. And really the key point is that we need to decarbonize as quickly as possible in order to prevent this sort of tumble effect that would create a basically irreversible change in our overall environment. And so with that in mind, that there does need to be a decarbonization of how we live and exist, what really is the impact that we're having with our human habitat? So if we start to look at what we have in terms of the construction industry, the operation and maintenance of buildings, we can see that this actually makes up almost a third of all global emissions in terms of CO2 equivalent. Historically, this has actually been an under-prioritized category. In the past, we've traditionally seen things like energy production and transportation be the highest priority, sort of the lowest hanging fruit in terms of applying strategies, applying budget and effort and time towards, because those did have an outsized proportion of overall carbon emissions. But as those have progressed and gotten better, we've actually seen the construction industry, materials, and all the impacts associated with those have actually increased as a proportion of overall CO2 emissions. And so what we've seen here is that as time has progressed and other industries have gotten better, materials are now becoming much more of a high priority for us to address in order to continue reducing our overall CO2 emissions. And so if we look at the industry as a whole, we obviously need to reduce CO2, but if we start to look at things on a building by building scale, we can actually see that the time value that we talked about with the decisions we're making today actually holds true when it comes to individual buildings. Building impacts have traditionally increased over time. So generally what you have is an initial cost in terms of CO2 with all the materials that go into building, the construction process, and then from there the building is occupied and continues to generate a certain amount of emissions for the energy that it uses for the maintenance and operation of that building. And so what here in this chart is we can see in sort of scenario one, if we look at a typical new building designed to code, we can see that there's a relatively continuous increase in overall carbon emissions over the course of its lifespan. If we now couple that with scenario 1A, which we look at perhaps decarbonizing the grid, so we start seeing more renewable energy enter the the overall market, we can see that the actual amount of carbon emissions tapers off over time and eventually reaches a point where it's no longer increasing because we've hopefully decarbonized the grid and are no longer creating any emissions. But there is still always going to be that initial emission impact that we have from just the materials themselves. And that's kind of what we see with scenario 2 here in a new net zero building. So even in a building where there's no energy being used, there's no energy being pulled from the grid, no operational impacts, we still see that there's a significant amount of carbon emissions that came from just the actual construction of that building. And if we compare that with scenario 3, we can see a retrofit where perhaps all the materials were already in place. We're not having to put new structure. We're not having to put in new foundations. You can see there's a significantly reduced impact. And then if you couple that with a decarbonized grid, then you start to see the significant reduction in overall impact. And the goal here is that to really reduce that initial value to start the game ahead, so that we're not creating these giant CO2 emissions in the process of actually creating a building, even if it is going to eventually be a net zero building, or perhaps even a carbon negative building that's maybe sequestering carbon. So this is really where the push for understanding how buildings create CO2 emissions, what goes into these buildings, and how can we truly start to decrease these overall CO2 emissions and the impacts of the building overall. So the key to that is going to be materials. The construction of a building is inherently going to involve some sort of materiality, some sort of construction process, and with that, that's where we start to see the impacts. And when we start to look at the life cycle impact analysis, we start to look back to where those materials came from, where were they extracted, and what was the process that went into that. And with materials, we actually have a quite profound opportunity in the sense that we've been able to make great strides with reducing energy usage, with reducing the emissions from transportation. At the end of the day, what we're really doing is just reducing the amount that we're putting back into the environment. Whereas with materials, we actually have an opportunity to perhaps begin to sequester carbon, start to actually pull carbon out of the atmosphere by really making a push to use certain materials. And this would actually allow us to begin to remediate existing carbon emissions. So we can actually start to heal some of the things that have already happened over the past several decades. So there's a great opportunity, and this is going to really come down to material selection and an understanding of where materials come from, how they're used, and what is the actual cost of using different materials. And we're already seeing this in the manufacturers utilize the uniqueness of carbon sequestration. There's just an example in a carbon negative in 2017. They're by no means the only. So really what this kind of comes down to is that our climate goals require a pivotal shift from our materials being carbon emitters to being carbon sequesters. So with that in mind, it's a life cycle impact assessment. And in specific terms, it's a science-based quantitative analysis of the potential impact building materials have on natural resources, ecosystems, and human health. Generally, what we see today is that these are based on ISO 14044 compliant data sets, which is a lot of words just to essentially say what we're looking at is we're trying to look at the material all the way from the time it's extracted from to when it is either recycled or sent to landfill, and understand not just the energy that goes into that process, but also look at the byproducts, chemicals used in its manufacturing and production, and any of the byproducts that comes out of those. And this is not a new concept. Life cycle assessments are born out of the manufacturing corporate rules. They were originally used for supply chain optimization and to identify inefficiencies in production processes. So the goal here was for large companies to look at how they were acquiring their materials, how they were manufacturing them, and to find better ways to be more efficient largely from a budgetary standpoint. So their goal was always going to be to save money. But a lot of times where they were saving money, we've actually found that that's where efficiencies are. We're seeing that less materials are being used. And that has a significant impact when you start to look at an entire industry as a whole. So these initial sort of manufacturing and corporate concepts have now grown and expanded to encompass a significant portion of the materials today. And we're seeing that more and more materials are having these assessments and analyses done on them by assessors, as well as the companies themselves are now submitting their materials for additional analysis so that people can understand how the materials impact the environment around them. And one of the most direct outcomes of this is what we see with environmental product declarations. So anyone who's worked on a LEED project or a sustainable project will at some point at least been seeing an EPD as their colloquial. And EPDs are really just a life cycle assessment of a single material. So it's looking at how that material, where was it taken from, how is it manufactured, where did it, how much went into the production material. And so what we can see here is even on the front page of an EPD, we can see that they have several impact categories where they're breaking things down by atmosphere, water, and what they call here earth, but a lot in this case is actually the usage of fossil fuels and how much not just energy was used, but energy from fossil fuels. And so what we start to get is a whole view of how materials impact their environment. What we'll be focusing on for this presentation is really CO2. That tends to be the primary one when we start to look at whole building life cycle assessment. But there are multiple other categories that are considered and are incredibly important. So when we start to look at things like acidification of land or of water sources, or eutrophication, where we're adding too much nitrogen back into the environment and it causes algae blooms and it can cause ecosystem collapse. Those are all incredibly important things, but for the purpose of doing here today, we'll be looking at just the CO2 emissions because that tends to have the strongest correlation to sort of the overall broader goals of what we're trying to achieve with sustainability. And so as we start to see more of these products have this information become available, it helps us understand how products perform. And this will allow better design decisions. It helps us understand where to find impact reductions. And at the end of the day, as this information is pushed further and further, we start to see a market change where this becomes the standard and people understand the materials around them, and it becomes transparency becomes the norm. So, and that's what we want to see, is we want to see everyone providing information about how they made this metal wall panel, or how they made this CMU block. And so that way that we can understand whether or not to use those, or what is the cost benefit of moving to a material over another. And so as we've seen this sort of the market begin to change, and more materials are having EPDs or having these life cycle assessment information available, we have started to see tools come together that begin to aggregate this information so that we can understand it on a whole building level. And really what this is taking is it's taking hundreds and hundreds of tiny, and in some cases thousands of tiny, smaller assessments, and bringing them together to understand how an entire building affects the environment around it. And that's really where we get the whole building life cycle assessment. It's really just an aggregation of smaller life cycle assessments. And there's multiple tools that have begun to sprung up that have provided designers with access to this information and made it really accessible in a way that we can understand it, and we can begin to sort of simplify the output so that we can have actionable data. And that's going to be key for us to be able to develop better impact reduction strategies, because if we don't understand where we are now, we can't really understand how to be better in the future. And here are there's a lot of softwares available, but here are sort of the top 3 at the moment in terms of market share. Tally is a Revit plugin that essentially runs parallel to the design of a project in Revit and allows you to see how your project is performing throughout all the various phases, and you can even use it to start to look at different design iterations against each other to make decisions. Athena Impact Estimator for Buildings is built off of the Athena Institute's curated database of material information. And so this is sort of a self-contained external program that you input information from your building into, and it'll give you information about how it would perform. And one-click LCA is sort of the clearest connection between, in some ways, what a life cycle impact assessment is it's a EPD aggregator. So what it'll do is it'll take your model and go find EPDs for the different materials being used throughout the building, and help you put together a clear picture of how your building is performing, as well as you can start to make decisions about different manufacturers, different models and types of materials that you want to use in your project. And so as these tools have started to grow, in that same sort of vein of growth, we've seen that there's been a mainstream acceptance for these in green building frameworks. We've seen an encouragement from these different certification systems. So there's points and credits available for this type of analysis in LEED, Green Globes, and WELL. And in the case of particularly LEED, what we've seen is there's an encouragement just to quantify the impact of the building, particularly in LEED v4.1. If you can just show what the impact of your building is, there's a point available for that. But if you also want to take a look at making better decisions once you've quantified it and show some sort of performance improvement, there's points available for that as well. So the goal is always going to be to make buildings better, and to make it so that we're making better decisions and more informed decisions about how we're creating buildings, how we're designing them, and the material selection that goes into them. And so we start to look at how we set up a whole building life cycle assessment. There's a general acceptance of what parameters to include. That's in terms of the information being used, that's going to be pretty standard across the board. The databases that are available are all built off of the information that's coming out of manufacturers, or coming from the manufacturer's products and being verified by third-party assessment firms. But the primary parameter that's going to change between different certification systems is what parts of the building are included in this assessment. And this is generally going to be driven by your rating system or your project goals. So what we want to look at is, what is the goal of the project in terms of reducing its impact? Is the goal to reduce CO2 emissions as much as possible, in which case it may make sense to include everything? Or are we trying to sort of have a targeted approach to what the designers have control over, in which case we may start to look at targeting certain categories of the building to quantify. And so what we see with that is, if we take a look at how LEED has set up their whole building life cycle impact assessment parameters, we can see that they've taken the approach of looking at very key categories of the building. In this case, what they're looking at is the foundations, the structures, the exterior walls, and roof assemblies. And what we're seeing here is that essentially what we're looking at is the sort of core and shell of the building, so to speak, to borrow a LEED term. And what this does exclude is it does exclude the mechanical, electrical, and plumbing systems, interior partitions, and finishes. And the goal with this is really to focus on the building elements with the greatest longevity in order to create a more accurate assessment. And so and that really comes down to, when we look at foundations, when we look at exterior walls and structure, those things tend to not change much over the course of the life of the building. Whereas if we look at interior partitions, mechanical systems, even especially interior finishes, we start to see that those things tend to have a much shorter lifespan than that of a building, and will be almost certainly be changed out over the course of an entire assessment period. And that's not to say that they're not important. The finishes, the furniture, everything that goes into a building, there is an impact associated with each of these. And the main reason that these are not included in a LEED assessment is that a LEED assessment requires a 60-year assessment window. So we're really looking at these materials and assuming that they're going to assuming that it's going to be the same over the course of 60 years. So that means that a metal panel on the exterior of the building is going to be analyzed for longevity. And so and that goes into the assessment, and that some materials may not last as long as others. So, just because a material is cheap and has a low impact, it may need to, if you have a stucco building, you may need to re-stucco 2 or 3 times over the course of a 60-year period. So that would be taken into account in the assessment. And that's a bit, thankfully with those exterior elements, you tend to have a level of predictability that you just don't have with the interior elements. What we're probably going to see in the future is we will see these be added into future assessments, but likely on a different time scale, so that they may not require to be analyzed on a assessment. They're just viewed as an initial CO2, added to the initial CO2 number, but then not really analyzed for their longevity beyond perhaps 5 to 10 years. And that may be overly optimistic. That is something that is going to develop in future life cycle impact assessment. As it stands today, these are not included. So if we start to take a look to break down individual aspects of a building that are going to be assessed, one of the first and primary ones that's going to be assessed is the structure. The structure represents a significant portion of the building's impact, and it can vary widely between different structural systems how much of an impact that is. Structure is one of those things that has to be designed early on. You tend to not change your structure once you've made a decision to stay with, once you've made a decision. So this is where having a life cycle impact assessment for the whole building early on in the design process can really be beneficial, because what we see is that when possible, the wood structure is almost always going to be the lowest impact. And then that also has the added benefit of wood being a carbon sink material. So anytime that's possible, you would want to use wood, at least when you're looking at it from an impact standpoint. Obviously, there's different regional design requirements and different programmatic requirements. So, some larger buildings may require a steel structure for different bearing loads or for different programmatic requirements. And steel does have a much higher impact than a wooden structure, largely due to the energy-intensive production process. But it does benefit from the fact that it can be almost 100% recycled. So in terms of steel emissions, what we tend to see from steel is that it tends to be more of a tertiary emission from the processes that go into recycling it from some previous usage. And then in terms of the highest impact, what we highest impact always with is concrete. Concrete is an inherently high impact material. It just comes from the current way that we manufacture and process concrete, admixture different, the cement itself as well as the aggregate that goes into it. However, concrete is a very useful material, particularly in places where we see with hurricane zones. So there's going to be so we'll talk about a little bit later about how we can, if concrete is a necessary material on site, and it almost always is in some capacity, how we can make that the smallest impact possible with that, and how we can find low carbon concrete mixtures. And so when we look at reducing impact for structure beyond just structural selection, this is going to require a level of collaboration with the structural engineer. It's thankfully a lot of the impact we see are tied heavily to budget. And structural engineers already do a ton of work to try and minimize the amount of steel that goes into the building, just for purely on cost basis. They don't want to put more material into a building, have to, which lines perfectly with what we're trying to achieve by reducing the impacts of the building. And so this is going to be something we to work with the structural engineer to really leverage those visions to see what the alternatives could have been. Make sure that we're giving designers and engineers credit for the work that they're doing to minimize the amount of material going into a building. And then if we want to take it further, we can look into prefabricated structural systems. If we really need to move with it, if the program calls for a structure that has steel concrete, it's always worth it to look into some sort of prefabricated steel system or prefabricated concrete system. There's inherent efficiencies found in the fabrication of, or in prefabrication, just due to the massive amount and the repetitiveness of the processes that go into it. And there's can be found there, and that's something that as that impact assessor would want to have a discussion with the architect, with the structural engineer. And so this really becomes a collaborative process with the whole team to really understand how to make that decision and where it's going to fit best in the building. And if so, what are the extents of this that we can maximize it to. And so then once we've worked through the structure, one of the highest impact categories to be the foundations of the building. And this is almost entirely due to the amount of concrete used. The foundations themselves are inherently concrete just due to concrete's performance specifications and the fact that it is an incredible material for this purpose. But cement production is an extremely high impact process. So what we want to do is we want to quantify the amount of concrete being used, then look at the type of concrete being used, and then also additionally the extent of steel reinforcement, so that we have, because foundations do tend to have a concrete and steel element. And so once we understand that information, then we can start to look at how do we minimize and reduce the impact of concrete. And as it stands right now, the primary way that we can reduce the carbon emissions from concrete is going to be reducing or substituting out a certain amount of the Portland cement. Portland cement makes up the vast majority of all of the CO2 emissions just due to its production process. It's every step of the way, it's a high impact material. And so some of the best strategies we have today is to replace it with fly ash and slag cement, purely because those are also high CO2 emitting production processes, but they're the waste product from those. So those are going to, as it stands right now, a lot of those are going to exist anyway. So anywhere we can use that is a great opportunity to sort of leverage the already existing CO2 footprint of existing materials. And what we've seen a lot is that fly ash does provide multiple performance benefits over just a standard concrete mix, particularly in foundation applications. But it does require a certain level of sorry, that was too far. It does require some specialty to work with. So having a team that understands that if you're specifying particularly a high fly ash content, you need to understand the different drying times. You need to understand how things are going to affect the schedule in a way that you're not going to, reduce the efficiency of the building overall. Just by fly ash, you'll start to see reductions in the building footprint just due to the sheer proportion that foundations make up. And then once we started to look at sort of the skeleton of the building, the structure and foundations, we can start to look at the wall assemblies. And wall assemblies are really where designers are going to have the greatest impact in terms of their decisions on the building. Because while there's an enormous number of materials available, there's equally enormous variability in the amount of impact these materials have. Something like, so understanding the impacts of different materials to balance that against the performance of different materials is going to be really important to understand early on. And what we found is that when we work with us on a project or two, they begin to understand how different materials perform so that they can make sure that they use them in a specific way. Because almost all the materials that we use in the industry today have a place in design buildings. It just really comes down to the extents of it, making sure that we right-size things and that we're using things in a way that is adequate for the programmatic requirements that we're seeing. And a lot of times what we see with this is that a lot of the impacts that are associated with the wall assemblies actually integrated in with the performance. It's something that does need to be balanced. If we look at the amount of insulation that's used in a building, insulation is another high impact material due to it being a foam and in many cases a petroleum byproduct. So we really want to make sure that we're using enough insulation to ensure energy performance throughout the life of the building, but we also don't want to oversize the insulation to a point where we're using too much material and reach a point of diminishing returns. So this is really just another sort of factor to consider during the design process. And if we look at how different envelopes compare against each other, we see that as with structure, as with the foundations, steel is going to be one of the primary decider. Steel and aluminum are going to be primary deciders of how much impact comes from an assembly. Particularly when we look at something like a curtain wall compared to an EIFS or an exterior insulating finishing system, or like a stucco wall. We can see that a curtain, for the same square footage, actually has 7 times the impact in terms of CO2 emissions, with a whole range of different assemblies in between those two. And in some cases, this does match up well with the budget. And obviously, curtain wall is a very expensive exterior system. It tends to not perform as well in terms of energy efficiency. So there's already, this is just another reason to really make sure that when we're designing the buildings around us, that we make sure that we're only using these type of spaces where it's absolutely necessary, because we do want to have views and daylight in certain spaces, but we also don't want to have just a curtain wall facade for the sake of having a full curtain wall facade when there's some serious negatives with that. One of the things that does tend to, with sort of the budgetary linkage, is CMU. CMU is a very cost-effective building material. It's used very widely, and rightfully so. It's a very durable material. It's easy to get on site, but it does have, again, due to cementitious material, a very high CO2 impact. So this is one where it kind of goes back to the idea of education and making sure that there's an understanding that CMU has its places in a design, but we just want to make sure when we're CMU, it's for the properties that make CMU a good thing. So perhaps we're looking at shear walls, or we're looking at bearing walls, maybe we want to use CMU there, but not expand CMU to all of the exterior walls. Those are the decisions and discussions that can be had with designers early in the design process to make sure that we're really right-sizing the building, different assembly, and also choosing the correct material palette for what the architect, the client, and everyone else wants to achieve. One of the things that we want to look at, and it's very much in line with this idea of the curtain wall, of the glass and aluminum that goes into that, is to make sure that we have the correct to wall ratio. Windows tend to have a very high CO2 emission impact, just due to the fact that steel have very intensive processes. They're heavy. They tend to take a lot of energy to get to the site. Anyone who's worked with Windows knows that they're not light. So there's a lot of energy and time and effort that goes into making those products, as well as just training them to this. They also tend to need the most maintenance when it comes to the life of a building. So if you look at this chart, we can see that the vertical all the way to the left should be of the material. So you can see curtain wall far and away is the highest, but it also has a very high use emission. So that comes from the fact that you're going to be replacing glass. It's not always the most durable. It requires a level of turnover in terms of the amount of material. So you're adding material throughout the life of the building. And so that's something to keep in mind. And then as we get to the last category in sort of when we look at sort of the minimum level life cycle impact analysis for a building, we get to the roof assemblies. And roof assemblies are one of the most inherently difficult categories to find impact reduction in, mostly due to the fact that the design of roofing materials is meant to be durable. There's chemicals that go into making roofing, particularly roofing membranes, very durable so that they don't break down, because the goal is for them to not ever have to be replaced within a 20-year span. Or in the case of an EPDM membrane, perhaps 25 to 30 years, or even longer. These are just the warranty periods. And what we've seen is that a lot of the products that do have lower impact in terms of emissions, like a TPO, tend to have a lower lifespan. And that's just due to the fact that there's a link here between the fact that a membrane that's designed to last forever isn't broken easily, it's not made easily. And so this is something where material science is really going to come a ways in order to make this better. But at this point, there are options to show appreciable impact reduction. But right now, what we're doing is sort of to do less harm rather than do good when it comes to roofing membranes. And so what we want to see with that is this is going to be something that needs to be a discussion needs to be had with the design team early on. Is what are the needs of the roof? Is it something where you would be willing to go with the TPO membrane, or perhaps if it's a data center, maybe a PVC membrane that has a bit longer lifespan that you don't want to risk additional leaks or something? That's a discussion that needs to be had early on so that we understand what type of material to specify for the roof. Because when we start to look at how roofing membranes perform against each other, we can see that TPO roofing membrane does perform better than a PVC or an asphalt or EPDM membrane, but it's not as significant of a change as we would like to see for some of the performance gains that we're giving up. Something that we are seeing the gap closed as new TPO membranes are coming out. There's new technology being put into their production that's allowing them to begin to reach performance parity with PVC roofs. But it is a discussion that I've had with envelope commissioners they don't always like TPO membranes, and that's something that we want to make sure that we're not ever specifying something for a building that's not going to be the best possible material for the performance necessities of that building. And so that's, again, it's a balancing act that needs to be hashed out early in the design process so that people understand what the pros and cons of what the decisions that they're making. And so, however, though, if we start to look at the square footage of a roof, we can see that while there may not be a significant difference in between different roofing membranes, when we look at the proportion of overall CO2 emissions from the building, that you can start to realize some appreciable gain, some appreciable reductions in overall CO2 emissions for a building. So that kind of covers some of the strategies that are available to us right now in terms of how to make their decisions with the materials that we're selecting for our buildings. If we start to look forward, though, what are some of the things that we may be looking at in the future in order to really start to push this a bit further? Right now, we're very much in the quantification stage and understanding where we're at right now and making incremental steps in the right direction. And we reach a point where that reaches the point of diminishing returns, and we need to find something new to push the envelope even further and really make the difference that we need to in terms of sort of the broader picture of what we're looking at as we try to reduce our CO2 emissions as much as possible. And one of the primary ways that we can do that is increasing the usage of wood. And this is going to come through, this has already begun around the world. We're seeing projects beginning to look at wood with sort of a new light. We're seeing high-rise commercial projects beginning to look at heavy timber, both in Japan and Europe. And that's actually a very exciting thing to see because we're just understanding a material that we've used for centuries a different way and maximizing its efficiency and optimizing the way that we use it. But also, as we mentioned at the beginning, wood is a carbon sink material. So when we couple wood, building out of wood with sustainable sourcing, like an FSC type situation, that's where we start to really see the ability to make meaningful change without any sort of deforestation. The amount of wood that would actually be needed to take over a majority of the share of construction in, I believe it was the US and Canada, would actually be able to be, or it was, I think the world over, was actually capable of being handled by the wood resources in Canada without deforestation. So as we've gotten better with this understanding of how to use resources without depleting them, we're now reaping the benefits of that by having an expanded material palette when we couple that with material science. And particularly when we start to look at wood, not just in different arrangements, but also from a material science standpoint of processing. There's been studies done into how to densify wood and achieve similar performance capabilities to steel. So anytime we can begin to really push into that, that's where we're going to start to see the the most good, and we might actually begin to start pushing that beyond just impact reductions and starting moving it into impact remediation, so that you can actually look at the building and say not just how much CO2 did it not emit, but how much did it actually sequester. And so we may start to see negative construction in the future in a good way, where we are actually, each new building presents a certain amount of CO2 taken out of the atmosphere and moving us towards a brighter future. And in that same vein, we also can look beyond wood to other traditionally used materials like straw or fibrous materials that also represent a level of carbon sequestration capabilities. And when we couple that with new insulations, with new waterproofing systems, with current materials, we start to see that these materials are actually, while they've been used for centuries and they're not really considered to be a modern material, they actually do have a place in the modern design palette. And that's an incredibly exciting thing, particularly when we start to look at regional architecture, because in some cases we may not have access to large wooded forests, and if we can, anytime we can reduce the amount of transportation time, the amount of energy and resources that go into getting materials from one side of the continent to another, or even from one continent to another, we can reduce the amount of overall impact from transportation by just using materials that are available regionally. And that's going to really make a big difference when we start looking at the grasslands, particularly the central US, or we start looking at South America and some of the regions there. There's huge opportunities to take advantage of the natural materials that are there that happen to also be very fast growing. So using those on a large scale isn't going to contribute to deforestation or reducing the overall materials available to us. And then as we also begin to look into other future technologies, and couple technology with sort of older building materials, we can also look at things like 3D printing. And 3D printing right now is very concrete based, so in some ways it's inherently to a high impact material, but it also does ensure that you're only using the bare minimum amount of material needed. And when you start to look at it in terms of the way that we can form concrete, the way that we can use different concrete mixes, we can actually begin to reduce the amount of insulation needed in buildings, we can reduce the amount of structure needed in buildings, and this, in the end, may end up resulting in a situation where if we can get our concrete and cement production processes sufficiently reduced in their impact, we should begin to realize these with future technologies that come to 3D printing. And obviously benefits there when it comes, additional benefits when it comes to and time and all the other benefits that come from being able to print a building in a day. And that sort of brings us to the elephant in the room, so to speak, when it's concrete, which is concrete. And concrete is one of those things that it is an incredible material, and as a result is very established as an industry, and is used around the world, and its usage for the longest time was increasing, although we have started to see that the amount of concrete being produced in the world starting to level out. But as it stands right now, if we were to look at concrete production as the total amount of concrete production in the world today, if we were to look at it as on its own as a country, it would actually be the third highest CO2 emitter in the world, behind only China and the US. Which it is, and it's something that we are going to have to address in the future. And as I said, with the current strategies that we have, a lot of it is going to be taking other materials that do have high CO2 impacts but are already existing and trying to offset the production of any new Portland cement. The real difference maker is going to be is that we have to find a way to replace Portland cement. And there's already a lot of work being put into this, and there's some really exciting new developments in this when it comes to geopolymers and basically manufactured clinker replacements. And with that comes the ability to use different aggregates. As it stands right now, there are a lot of recycled aggregates that can be used. You can use crushed concrete in addition to any sort of natural stone. But as we start to gain a better understanding of how cement works and how to replace it, we can start to broaden our spectrum of the type of materials that we can use as aggregate for concrete. And the goal would be to eventually be able to hopefully use the material from the site as the aggregate for a building. And a lot of work being put into this by agencies like NASA and companies that are looking into space exploration, particularly because you can only bring so much material with you when it comes to interplanetary or interstellar travel. And that's something that I think we're going to see the benefits of in our local industry as well. And so that's one of those very exciting developments that we want to keep an eye on. As it stands right now, it is a future development, as a lot of the products themselves are at the very least untested when it comes to the long term, and in the worst cases aren't quite on performance parity yet. So they're still in the development stages, but it's something that we as a society and as a species really need to get on top of, and we are moving forward there. So in terms of how we design buildings, the decisions we make now matter. We can make an impact today with the decisions we're making in the buildings that we're designing, and a lot of that comes from an understanding of the materials that we're using. And that information is out there today, and when we start to look at it on a whole building scale, we start to really understand how different design decisions will affect things on a very broad scale. And as that information becomes more available, we can start to understand an entire industry in a way that will push the market forward so that we can get better materials. We can really start to demand that manufacturers have better practices, that the way things are working now for what we need in the moment, but does not have a place in the future. And that's really going to come down to better efficiency on manufacturers' part, better transparency from them, and we're already seeing that changing today. And so really, that assessing impact is the key to making better decisions. And for every building that we quantify, every material that we quantify, we gain a better understanding of how our construction industry has an impact on the world around it. And every little impact reduction matters, because at the end of the day, when we aggregate those together, that's where we start to see the impact reductions that we need in order to meet the goals that we've set for ourselves as a species in order to prevent climate change. So, and the good news is that we are improving at this, and that the information that's today is better than it was yesterday, and it's going to be, and next year it's going to be better than what we did. And being a part of that is very exciting, because we get to take part in making the world around us a better place. And so I just wanted to leave you off with sort of the challenge and also the encouragement that carbon neutral future is possible. And I really liked this quotation from Eduardo Seta de Moura, where he says, "There is no ecological architecture, no intelligent architecture, and no sustainable architecture. There is only good architecture. There are always problems you must not neglect. For example, energy, resources, costs, social aspects. One must always pay attention to all these." And that really in many ways sums up what we're talking about here. Is we want to understand what we're doing when we make decisions, and how our designs affect the world around us. And whole building life cycle impact assessment really goes a long way towards providing that information for designers. So I think that was a lot of information. So I want to take a